morning. In this session, I would like to demonstrate simulating a distillation column. In fact, you will be able to observe when we go into Aspen, there are two shortcut model to design. The other one is a rigorous model which will be operating in rating mode. So the problem is you have a feed coming at the rate of 1 kilomole per second with 40% propane and isobutane. The temperature and pressure are given here. You need to obtain 96% mole fraction of propane in the top product, 99% of isobutane in the bottom product. So the column is operating at 20 atmospheres. So let us see how to simulate a distillation column. I will try to introduce both the models in the same demonstration. So let me define the components first, isobutane and propane. Call it as IB. So having defined the components, choose a property. Go to next, simulation environment. I'll show you later. I'll try to add another column later. So I'll be using a duplicator block. And then when you go into columns, you can see there are models. DSTWU, you can see it's a shortcut distillation design model using the Win Underwood Gilliland method. Whereas this one, RADFRAC, is a rigorous distillation model which is going to operate in rating model. So I'll try to demonstrate both of them in this demonstration. So initially, let us take the shortcut distillation model. You will be advantage of simulating using shortcut distillation, though it may not be very accurate because you are using certain formulae, Win Underwood Gilliland correlations to calculate or design the column, which may not be really very accurate, especially when you are dealing with systems. So having defined this, let us go and try to complete our problem definition. Take the SI system of units. The feed is entering at 322 Kelvin, a pressure of 20 atmospheres, of 1 kilomole per second, having a composition of 40% propane, isobutane. So having defined the stream, now let us provide some details with respect to the column. Now you can see when you are trying to normally design a column, find the reflux ratio as somewhere between 1.2 to 1.5 times the minimum reflux ratio, right? Of course, if you specify the number of stages, it will calculate what is the reflux ratio required to obtain the given purity. So let me choose the heuristic. Once again, you can observe here, if the value that you are providing here is less than -1, let's say for example -1.2, then it means we are using a reflux ratio of 1.2 times the minimum ratio, right? So if you want, you can use any other value as well. Now you are trying to select the light key, propane being more volatile, it will be the light key in this binary system. Now you can see what do you mean by recovery. This represents moles of light key in distillate divided by moles of light key in feed. For example, propane is entering into the column, how many moles of propane should be there in the top product. So for example, let's say it is something like 0.95. You can change whatever recovery you want depending on the purities that you are expecting. Similarly, the heavy key is isobutane, but once again be careful here. This recovery of isobutane is also defined with respect to distillate only, not the bottom. So I can say, for example, 0.4. See, remember, this total need not be 1. According to these recoveries that you are specifying, we are asking the simulator to put 95% of propane coming into the column into the top product and only 4% allowed into the top product. What will happen to the bottom? 5% of propane and 96% of isobutane entering into the column will go into the bottom product, right? So if you want, you can vary these recovery ratios. Remember, this is a design model. That's why we are specifying the input, output, whatever purities that you are expecting. Though these values don't reflect the purities, remember the recovery ratios of both the top product as both light key as well as heavy key are going to influence the mole fractions. So you may have to change these recoveries if you want to obtain a particular purity. But this is a shortcut model, so though it may not be very accurate, so there is no point in doing that simulation to obtain a particular purity, which we will be doing. If you are interested, you can also do it here. For the time being, I am assuming that there is no pressure drop across the car, right? So having specified this, let us see what will happen. You have already talked about all the required input, so let us go to the next. Now you can see the stream summary initially. Now see, out of 0.4 kilomoles per second, 95% of that should go into the top product. The remaining automatically goes into the bottom product. Similarly, out of 0.6 kilomoles per second of isobutane, we wanted 4% of that to go into the top product and the remaining go into the bottom product. And the mole fractions, the purities that you are able to get are about 94% propane in the top product and 96% isobutane in the bottom product. Okay. What about the column details? So let us look at the results of the column. Now you can see the minimum reflux something like 2.6. You know what is meant by minimum reflux. The actual reflux ratio, we have already specified this as 1.2 times the minimum. You can check it out. The minimum number of stages are calculated as 11.3. Actual stages are 22. Right? What do you mean by minimum number of stages? When you are operating the column at total reflux, the number of stages will be minimum. So this is the feed stage, almost 12, and you can see deboiler duty, condenser duty, and other details. Now, just show you one more iteration, then we can probably go into the other. Suppose if we already know the minimum reflux is 2.59. Let's see a value of reflux ratio. Any value greater than 0 will be taken. Right? Let us see what will happen to the column results. Now you can see what will happen to the number of stages now, because you are operating very close to the minimum reflux ratio. The minimum the stages are going to be very, very high, 300, right? So this is the problem. Now in the same way, if I try to operate the column at a very high reflux ratio, let us say 2260 or something like that, then what will happen to the number of stages? It will almost approach the minimum number of stages. Putting everything back into the column, practically operating that under total reflux condition. So these are the two extremes with respect to reflux. At one end, the number of stages will be low. At the other end, the number of stages will be very high. That's why in one case, the capital costs, the fixed costs are going to be higher, the operating costs may be lower. The other case, the fixed costs are going to be higher, operating costs are going to be lower. So obviously there is an optimum reflux ratio that exists. So let me go back and reset my simulation to the same value of minus. We already know the minimum is 2.6, so let me now consider 3. Now before I go into the other model, let me show you now. I'll be using a sensitivity analysis, say new. Okay. I would like to vary the reflux ratio. It's a block variable. Block is V2. Variable is reflux ratio. You know the minimum is 0.6, so I'll start with 3 to maybe 30 with increments of 1. Right? I would like to see the effect of changing the reflux ratio on some variables. So let me call number of stages. It's a block variable. Block is V2. Variable is actual stages, calculated number of stages. Similarly, let me see what is the top product purity. In variable, mole fraction. Stream is what is this stream? The top product is S3. Variable component is propane. So this is going to represent the mole fraction of propane in the top product. Similarly, bottom product purity. Also a stream variable, mole fraction, bottom product which is S4, component isobutane. So let me put one more, let us say reboiler duty. If you want, you can add as many such variables as you want. It's also a block variable. Block is B2, variable is reboiler duty. The next fill variables and then run. Now you can see, don't worry about this, you can see the results of your sensitivity. Now what is happening, as you keep on increasing the reflux ratio, you can see that the number of stages are coming down. So at a very large reflux ratio, the number of stages will automatically be very close to the minimum number. And you can see the top product purity and bottom product purity are constant. So the reflux ratio is not affecting the purities. Be careful about this observation. Remember, the model that you are working with happened to be operating in design mode. So we have already specified the required recoveries. We wanted to put 95% of propane entering into the column in the top product, about 4% of isobutane in the top product. For achieving this purity, whenever you change an internal operating conditions like reflux ratio, it will try to calculate the number of stages required to obtain this kind of purity, specified purity. And you can see as you keep on increasing the reflux ratio, the reboiler duty increases. This is of course obvious. If you want, you can also observe the results. Let us see, top product purity and bottom product purity are not affecting. So I'll try to see what will happen to this. Now you can see the number of stages. This is the scale for number of stages. Is really getting influenced between 3 to maybe around 20. After that, more or less, it is very close to the minimum number. Now you can see what is the effect of reflux ratio on the number of stages. Similarly, you can see what is the effect of increasing reflux ratio on the reboiler duty. Reboiler duty continues to increase more or less linearly with increase in reflux rate. So we were able to get a particular purity of 94% and 96% with respect to propane and isobutane, respectively in top product as well as bottom product. I don't want to fine tune this design because this itself is a shortcut design model. Now I will try to introduce and try to do that fine tuning in the other model, this being very accurate and rigorous. But the problem is this DSTWU is a shortcut model, design model, whereas this one is a rating model. It's a very rigorous model. In fact, you will be able to do many calculations using this. You will be able to do reactive distillation, azeotropic distillation, any type of non-ideal feed. You can have number of input feeds, number of side streams, number of pump arounds. So any complicated distillation problem, more or less, you should be able to simulate using this RADFRAC model. Now, let me connect. Because I am taking another output from duplicator, the same input provided to DSTWU is also given to this RADFRAC model. S6 and S7 are the top and bottom products with respect to this RADFRAC model. Because the feed is already defined, we may have to specify some details with respect to this RADFRAC model. So the problem with RADFRAC, if you have started with RADFRAC directly, it may be difficult for you to provide some of these results or some of the starting values for these results. However, if you have the results of the shortcut model, it will serve you to provide the necessary input for the RADFRAC model. So I always suggest you start with a shortcut model. If you are not very clear and experienced, get some preliminary data. Use this data to fine tune your design using the RADFRAC model, that being very accurate and complex So the number of stages you can observe from here 23.54. So let me take maybe 24. Condenser, let us take total. Distillate rate. So how do I know distillate rate if I directly start with RADFRAC? But I get some estimate from this. Distillate to feed fraction. Remember 1 kilomole per second. So distillate to feed fraction is 0.4. So what is the distillate rate? 0.404 multiplied by 1. D by F in other words. Right? So I'll provide this value 0.404. And ratio, I think we were using a reflux ratio of 3. So let me use the same value here so that we can compare the results of both these columns. Say next. Feed stage location, again you will be able to see some idea about 12th stage. So you can specify that here. So next. Though this may not be very correct, I am trying to assume constant pressure as I did with respect to the previous column. I mentioned what is the difficulty with this assumption. Anyway, go to next. So that is continuing. I should have deactivated that model. What are the results? Remember S3 and S4 are shortcut models, shortcut design, whereas S6 and S7 are the rigorous distillation model. Look at the stream summary. I will add S6 and S7 so that you can compare. Now, you can also look at the other details when you simulate. We are able to get a purity of 94% from the shortcut model. More or less giving the same data, we only got to a purity of 91%. So you can observe the difference between these two. Remember, this is going to be based on some shortcut equations with correlations. But here, this is more accurate and very rigorous, right? So before I switch on to the other issues from our problem statement, I would like to once again conduct a sensitivity study in this model. So I go to instead of B2, now I'll be doing the calculations on B3. Once again, I will be varying the reflux ratio. Here I think it is represented as mole RR. Specified molar reflux ratio. So let us say 3 to 30 as we did in the previous column. Really, now I will define all the variables with the block. This is instead of B2, now it is B3. The number of stages are represented here as I think n stage. Right. Then top product purity. Fraction. Top RADFRAC column is S6, component is propane. Similarly, bottom product, this is S7, isobutane. Reboiler duty, it is again B3. So more or less the same type of sensitivity I am performing. I am trying to change the reflux ratio and would like to observe what is its effect on the number of stages, top product purity, bottom product purity, and reboiler duty. So let me run this problem. Reset and run. Results. Now try to compare what was happening in the sensitivity. So as you keep on increasing the reflux ratio, remember we have already specified the number of stages, which is a prerequisite for product, right? What is happening to the top product purity and bottom product purity? They are increasing as you keep on increasing the reflux ratio, right? So you can see as you keep on increasing the reflux ratio, the purity of propane as well as isobutane in the bottom product are increasing. But the course, the reboiler duty increases like what you have seen in the previous case as well. What was happening in the case of the sensitivity on DSTWU column? For obtaining a given purity, purities were constant because they are defined by the specified recoveries. It was calculating the number of stages in order to obtain the specified purities, right? The number of stages were changing, but the product purities are remaining constant and the reboiler duty continues to increase. Now you can of course see the results curve and try to observe the number of stages are constant. Of course, reboiler duty increases like what you have observed in the previous case as well. More or less, they are coinciding with the top and bottom products are more or less coinciding. Now you can see as you keep on increasing the reflux ratio, this is changing with respect to top product, the left hand side scale, bottom product with respect to the right hand. Right? If you try to change this number, maybe there can be a difference, but doesn't matter. So depending on whatever purity that you want, for example, if you want to keep the number of stages constant, and if you would like to obtain a purity of 0.98, now you can practically observe what should be the reflux ratio that you have to use. Right? So around 4.5 or something like that. You can always use a design spec to fine tune whatever is your requirement. But try to observe the difference between what has been specified, what is being calculated in both these models. Once again, let me concentrate on that. Remember, this is a shortcut distillation design. So in this case, we are specifying the feed stream. We are also specifying the purities of the top products and bottom product, though exactly not mole fractions, the recoveries in terms of recoveries, and we are specifying the reflux ratio. Then it was calculating the number of stages, feed stage location, the minimum reflux ratio, the actual reflux ratio, and some other details, reboiler duty, condenser duty, and so on. Remember, this one is a rating model. In the case of rating model, we have to specify the input streams, the column, like reflux ratio, number of stages, feed stage location, pressure, all such things. Then it will try to calculate the product purities. Observe the difference between what was the input for a design model, what was the input for a rating model, and what is being calculated in the case of design model and what is being calculated in the case of rating model. Now let me go back and probably show you. This is what we require. I thought there is no point in doing this calculation on the shortcut model because it is accurate. So I would like to do this calculation on the RADFRAC model. Let me deactivate this. You know how to use this. We have been using this design specs several times. New. So what is that we want? We want top product purity. We define like what I have done earlier. It's a stream variable, mole fraction. S6 is the top product from the RADFRAC column. Okay. What is my requirement? TPP 0.96. Tolerance maybe 0.001. What is that I would like to vary? Of course, you can vary the number of stages for a given reflux ratio, or for a given number of stages, you can vary the, for a given number of stages, you can vary the reflux ratio, or for a given reflux ratio, you can vary the number of stages. So either way, it's up to you. You can try both options. So I'll take block variable. Block is B3, variable is small r reflux ratio. We have already observed what is the effect of changing the reflux ratio on the purities in the sensitivity. Right? Let us say some 3 to 30. This is where I expect the solution to be. Next. We got to a convergent solution within 6 iterations using secant method. You can see the results. So when we started with a reflux ratio of 3, we were able to get a mole fraction of 91% with respect to the top product. But when the reflux ratio increased to 4.42 for a specified number of stages of 24, we were able to get a purity of 96%. Of course, you can also see this from the stream summary. I'll specifically see the results of this column. not writing because of the design spec. Same result. Are not being represented. I don't know. Normally, you should be able to see the mole fractions. Let me see this. What is the purity of the bottom product? So you can check up, and if you think that the mole fraction of bottom product is also required to meet 99%, you can once again use a design spec. Let me use that also to show you. Beyond that, there may be other calculations that are required. So let me, we know now from the design spec results what the product purity that we want, 4.42. Let me do this directly and see what is the effect on the bottom. So the reflux ratio, instead of 3, I'll be using 4.42. And deactivate this design spec, delete this design spec. Set and run. Now let us look at these results. I don't know why the results were purged earlier. It's not showing anyway. It's normally. Why this is happening? Let's see. So delete the sensitivity. Now no longer we require the first model. So in none of the models, these mole flows are represented or mole fractions are represented. Normally this should not happen. Maybe you can try. This is one aspect. If you are interested in obtaining a particular purity, if you are not getting with this specification, you can use once again another design spec. The defined variable will be the purity or mole fraction of isobutane in the bottom product. Vary, we have already varied the reflux ratio. Maybe vary any other variable which is going to have an effect on the purity of the bottom product. For example, distillate rate. Remember, reflux ratio and distillate rate may be dependent on each other. Now, when you put these two variables as vary, so the simulator has to find out a convenient result which is going to satisfy with both the requirements. Normally, you should be able to do this. I would like to show you some of the other aspects that are involved with the model, which are quite good. Of course, you can elaborate them when you go into your details. This is block B3. Click on block options now. This is design and specify column internals. So you can see what basic things you would like to specify. Stage is 1. Start stage is 2, because the column 1 is going for total condenser, and the total number of stages we have defined, I think, is 24. So if you are using reboiler, this should be 23. So we have done this. I'm giving minimum number of specifications. Maybe you can try to see the other details. Next. What happened? Already you can see the packing height is obtained as 6.6096 meters. The diameter is 5.309. Number of passes. We have taken a tray column. Tray packing type is C. You can change whatever you wish and try to design this column. Once again, if you go and see the details, what is that you have? Balance, split fraction, duty. You can see this internal sections, CS1 results. Some of those results that you have calculated, the diameter is about 5.5, the total height you can see. So all these details you can check it out. Please verify, though because of lack of time or the increase in the video time, I would like to confine myself, but you can explore some of these possibilities, right? And you can see the geometry. So according to your design, the geometry details are also provided. So design parameters. So what is the flooding and other details. If you want, you can vary and try to see what will happen to your geometry and design, right? One more thing that I am interested in showing is the profiles. So as I said, this is a very, very comprehensive model. So you can probably look at some of these profiles calculated. Would you like to see the profiles of propane and isobutane in the liquid as well as vapor? So you can select. So this is how you can observe what is liquid, what is vapor, how the composition of these components are changing from stage 1 to stage 24, because this is the total number of stages we have given. Similarly, you can observe what were the other profiles that are available or plots that are available. You can see composition, flow rate, pressure, K values, relative volatility, flow ratio, and so on. Right? Please try to observe some of the details. Now you can even go into the design of a distillation column. Of course, I have not selected different types of distillation columns, tray column, sieve tray, or bubble column. You can select and try to design whatever you are interested in. So this model, as I said, is very, very comprehensive. So you should be in a position to design much more rigorously compared to the shortcut distillation design that you are. Shortcut distillation design will help you to get some preliminary data with which you will be able to start by simulating this RADFRAC column. If you want to get the required purities, either manipulate some of the variables in order to get to your required purities. So that is going to be your design calculations. So with these remarks, I would like to conclude this session.